So my name's Arne. I'm from Europe, but I flew in because met Daniel in Berlin recently, and he told me about this awesome meetup. So I was like, yeah, gotta check that out. So been here just long enough to get over the lightheadedness. Yeah, I do Clojure consulting and training. I also make screencasts about Clojure. I don't know if anyone's seen Lambda Island, lambdaisland.com. You can find like videos about Clojure.
I heard there's even an article there that maybe someone around here wrote. Yeah.
That is true, yeah. The Den of Clojure speaker, Joanne Cheng, wrote an article about D3 and ClojureScript, which is really neat.
Awesome.
Yeah.
Cool. Well, thank you for joining us all the way from Berlin.
Thank you very much for having me.
Yeah, pretty cool to come down here. And you're going to talk to us about zippers.
Zippers, yes, functional zippers.
It's a fun term, isn't it?
Who's used zippers before?
Take it away.
A couple people, okay. All right, yeah, so I got a lot of slides, so we're gonna keep the pace. Gonna put on a timer so I have a rough idea. If I really go over time, I'll cut it short, but we'll see how it goes. So yeah, welcome to my talk, The Art of Tree Shaping with Zippers. So you already know who I am now. I'm Arne Brasser. I'm Plexus on the internet. I'm from Belgium originally, tiny country in Europe between France, Germany, and the Netherlands. Beer, chocolate, waffles, fries, mussels, all the good stuff. But I'm currently living in Berlin in Germany. And I do, like I said, Clojure consulting and training for a living, as well as this thing, Lambda Island. So there's tons of cool screencasts on there. Been going for about 2.5 years. There's 40-something episodes there. It ranges from, core stuff like transducers or small stuff like the sum function, but also, datomic, reagent, reframe, tooling, ClojureScript compiler, integrant, you name it. There's 40-something episodes on there now. Some of them are free, some of them you can buy, and then you can also just sign up for sort of an all-access pass. So yeah, that's me. Agenda for today is we're first just going to look at Clojure Zip from a user's perspective. Just kind of walk through some examples, what the API feels like, what you can do with it. Then we'll talk a bit more about, okay, what exactly is this whole functional zipper idea? Where does it come from, and why does it matter? Why is it relevant? Then we'll look at how Clojure implements zippers. And then finally, very briefly, I'll touch on a couple libraries sort of that build on zippers, stuff that you can go from there. So the Clojure Zip API. To talk about before I can really show you examples, you need some kind of mental model of what we're talking about when we say zipper. So a zipper, also called a lock or location, is kind of like a two-element tuple, where the first one is some kind of tree-shaped data structure. Can be all kinds of things, but anything that sort of has nodes with children. And then the second one is a kind of a pointer to a specific node, like a way of focusing on a specific node. Or you can also think of it as, a path in the tree to say, like, okay, now we're dealing with this particular one. So like as a metaphor, you can think of it if you have like, a map with a dot saying you are here, like the map plus the dot, that's your zipper. With the difference that when you have that zipper, you can move that dot around and make changes to your map, but we'll get to that in a second. So the zipper API allows you to navigate in your tree. You're looking at a specific node, and then you can say you want to go up, down, left, right. And then when you end up at a certain location, you can start making changes. Now, when I say making changes, it's Clojure, so it's all immutable, like Clojure's own data structures. So it really just means that you get a new copy, right? A new version, sort of an updated version of your zipper. Same with the navigation. It's all sort of in a functional way. I mean, if you're used to how Clojure works, this should be quite natural, but we're pointing out that when I say replace or remove, or it's all, it's functional still. So Clojure zip comes bundled with Clojure itself. You don't need to install anything extra. If you have Clojure, you have Clojure zip. You just need to require it. It's quite typical to require it and call it Z. And then there's a couple different functions to take a data structure and sort of turn it into a zipper to sort of wrap it into that two-element tuple. So for instance, if you have nested vectors, you can think of nested vectors as being kind of a tree structure. So if you say then vector zip and you pass it that vector, you get the zipper or the lock over that vector back. So I'm using all these terms kind of interchangeably. We'll look more at where the term lock comes from when we talk about the origin of the zipper idea. Now a tree, like I said, a nested vector can be considered a tree. A nested sequence can be considered a tree. XML documents are quite naturally a tree. So you have an element has children, and then those elements can have their own children. But anything that has nodes and child nodes can be a zipper, and we'll look a bit more about how that works when we look at the Clojure implementation. So I'll walk you through a very simple example. So here I have a vector, and I've turned that into a zipper. And so on the right-hand side, you kind of see a visualization of what we're looking at now. So we're looking at that vector as a tree, and we're pointing at the root node. That's why that top node is colored blue. So that's kind of, that blue is your dot saying you are here. And then you can go down. Now we're just looking at that first subvector. You can go right, can go down again. You can go to the rightmost sibling on the current level. And then when you end up at a certain point, you can do these operations. For instance, you can append an extra child node to the current node. So now I've appended an extra x, and you see that now this node, instead of just 4, 5, now it has 4, 5x. And then you can go up again. Now at some point, so all of the time, so you see I'm threading this. The result of each function call is a new zipper. Now at some point, you want a plain value again. You want the value of the node you're currently looking at. So that's why you use what you use the node function for. It sort of just gives you, sort of takes the node that you're currently looking at and gives you the value of that node. And it's also very common that you just want to go all the way back to the root, all the way back to the top. So you say up, up, up until you can't go up any further, and then get the value of sort of the complete structure. So the combination of that is encapsulated in the root function. Yes?
Is it required if all the sort of values you might want to be associated with something are held in the leaf nodes?
Can you repeat the question?
Sure. Microphone? Okay. The way you drew that,
Yeah.
the leaf nodes had an atomic value,
Yeah.
and everything else had a path value. Is it required that only the leaf nodes have atomic values associated with them?
Well, the only requirement that the Zipper API has is that for whatever structure you give it, you can define what is a branch node and what is a leaf node, where a branch node is anything that can have children. So in this case, when you're using vector zip, it's going to consider anything that isn't a vector as a leaf. But you can define that however you want, but you do need sort of that dichotomy of, it's either a branch or it's a leaf. It can be both. Does that answer your question?
Somewhat. Can a branch have a distinct value separate from its path?
Yeah, I'm not 100% sure what you mean by that, but
If you have built a tree structure,
yeah.
and you may have things branching out based on their value compared to what this node is. Think about a binary switch tree.
Yeah.
The branch nodes actually have a value. The leaf nodes have values.
Yeah. So you can have extra values on that node. Like say an XML document, an element has attributes. Absolutely, yeah. So yeah, that is okay. You kind of don't see that in the vector example because a vector doesn't contain much more information besides its children. But yes, a node can have extra information besides its children. Absolutely, yeah. And we'll get to that now. So here's a second example. So I kind of came up with some hypothetical XML. So this is a representation of a shopping cart, which has line items and a customer. And then the line items, there's 2 product line items, a discount. And so in Clojure, Clojure has sort of XML parsing built in. So I'm using Clojure Java I/O to read that file, and then Clojure XML to parse it from XML to a Clojure data structure. And then the result is something like this. So this is how Clojure XML represents XML documents. So it uses Clojure maps and vectors, where each XML element turns into a map which has a tag, attributes, and content, which are its children. And when you get something like this, then you can pass that to the zipper XML zip function, and you get, again, a zipper over that XML document. And so this is now, yeah, it's getting a little small here, the visualization. But so the top one, for instance, says cart, and then its 2 children says line items customer. So this is a representation of that XML that we just saw. And I can do the exact same thing. I can go down, right, leftmost, down. And now I can replace a node. So before it was a string node that said chocolate, and now I replace it with luxury chocolate. And now I go up, and then I use the edit function. The edit function is like update or swap or any of these functions that you take a function that you apply to a value to get a new value. So in this case, I'm going to take the value in this node and call assoc in on it to, in the attributes map, assoc a new price, because now it's luxury chocolate, so the price has gone up. And so before it says price 2.5, now it says price 2.9. And then I'm done, and I go back to the root, and I get the root value. So this is kind of, I mean, of course, you don't write code like this, where you just say, down, left, right, replace. Like this is just sort of an, you're gonna wrap this in functions that actually check where you are and what you're doing. But conceptually, this is what you typically do. You walk around your tree, you make changes, and then in the end, you kind of go back to the root, get the root value. That's kind of how zippers work. So you've seen most of the API already. I'll just quickly run through the full API. It's not that big. So there's a couple different ways to create zippers. We've seen a few of those. There's these different functions to navigate. We've seen all of these. There's a bunch of functions to update. We've only seen a few of these, but it's basically insert a sibling on the left, insert a sibling on the right, insert a child on the left, insert a child on the right, edit, so apply a function to the current node value, remove the node, replace a node with a new node, and then there's kind of a helper function which takes an existing node and a new set of children, new sequence of children, and creates a new node which has all the attributes of the old node, but with a new set of children. And we'll get to that again later. You'll come across the make node later when we talk about the implementation, why that is interesting. And then finally, you can sort of look around, right? So you end up at a certain point, and you can say, what are my left siblings? What are my right siblings? What are the children of this node? You can ask for the path. This gives you a sequence of node values from the root up to your current node that you're currently looking at. And then you can just ask, is this a branch node or not? And then finally, there's kind of these 3 functions which come together, which give you a straightforward way to do a complete walk of all the nodes in your tree. So this does a depth first walk. So you start, I'm using iterate. If you're not familiar with iterate, it really just, it says, take cart zipper and then apply the next function to it over and over and over again, and then it returns a lazy sequence of all the results. So here I've applied it 0 times, so I'm still at the root, and then 1 time, and you see it starts going down, to the next one, and then when you get, it's depth first, so it goes to the bottom, and then the next one, it goes left and up, until you've seen every single node in the tree, and then if you go next 1 more time, it goes back to the root and adds a special marker to that zipper that says that, this is the end point. So now you can use that end predicate to say that, okay, am I done walking? Am I done checking every single node? So now you know the complete zipper API, and I could end my talk here, but I still have a lot of interesting things to talk about. So first of all, I'm going to give you a couple caveats. Now, you're going to probably forget these, but hopefully when you actually get into the thick of it, and you start banging your head against the wall because something isn't working the way you think it should be, then maybe at some point one of these is like, oh, actually, this is what Arne mentioned. This is this one thing that I should watch out for. So the first thing is that there's no boundary checks, so don't fall off your zipper. There's no way back from end, and zippers are not cursors. And I'll go over these one by one. So no boundary check simply means that if you go down, down, down until you get to a leaf node, and you go down once more, you get nil. And up to that point, all is well, but then you do one more thing and you get a null pointer exception, and you need to start looking like, okay, where did that nil come from? Now this is how the API is designed, also left, left, you go left one more time, you get a nil. It means that you can do stuff like this, if let, left, if I can still go left and do something there. So it's a fine API, but it is something to, you do want to have some checks and assertions in there to make sure that you don't need to start chasing your nils after the fact. The second thing I wanted to point out, so I said, okay, when you do this complete depth first walk of your tree, you get this special end value, and that end value is in a way a zipper, but not everything works on it the way that it works with other zippers. So for instance, if you try to go to the previous node again, it's just going to give you nil. And the main thing here, main advice here is like this end, either just treat it as a sentinel, just as a way to say like, okay, you're done, or to get the root value back, but that's kind of it. Don't try to do too much with that. And then finally, zippers are not cursors. What I mean by that is, a cursor in text points in between two characters. And that means that it can be at the beginning of a line or at the end of a line, or it can be on an empty line, whereas a zipper always points at a concrete node, which means that, for instance, a zipper you can't have a zipper inside an empty collection and then say, okay, now I want to insert something here. Which, I mean, that's how it's worked. There's nothing wrong with that. But depending on the kind of problem you're solving, sometimes the cursor model is much more intuitive, and so you kind of start thinking of your zippers as cursor because it kind of, the metaphor kind of matches until it doesn't. So here's a little example of, say, naively, I wanna take this nested vector, go 2 levels down, so I'm inside the nested vector now. I want to remove that 1, remove that 2, and in place of it, insert a 3. So what I'm kind of hoping for is a nested vector with a 3 inside. So let's see what happens. I go down, I remove this, and now I'm looking at that middle node. That might already be a little bit surprising. This is 100% by design. Again, there's nothing wrong with that, but you do need to know how this stuff works. So remove says that it removes the node at your current location, returning the lock that would have preceded it in a depth first walk. So that means over here, if you would have called that previous, you would have ended up in that middle node, and that's why it gives you that middle node. And so if we continue our example, you remove it, you try to do an insert, and now you're trying to insert a sibling of the root node. You can't have a sibling if you don't have a parent, and so it's going to say exception insert at top. So that's something to watch out for. And this is even more obvious when you have an example like this. I'm looking at that 1, 2, and then I delete it, and now I jump to that y. Sometimes a little counterintuitive. All right. Any questions so far? Yes.
Are you familiar with something called XPath and JPath? And if so, have you found them to be useful compared to those ways of navigating data structures?
I mean, XPath, I've used XPath a long time ago. I mean, conceptually, it's not too different from, say, a CSS selector, right? So I think having these kind of selector APIs are very useful. I think they both have their uses. So for instance, say I'm doing stuff over XML, I will very often use nlife, which kind of gives me that selector API. it just kind of depends what you're doing. There are cases where the zipper model works, where you really sort of need more context, or where it's sort of more loosely defined. Not everything can easily be captured in a path or in this kind of expression. So I think for those cases, this is a really great tool in your toolbox.
So you mentioned that the pointer has to point to some node. So does that mean when you create a zipper, you have to give it a root node, or do you create the tree first, or how? When you create a zipper, how do you do it?
Yeah, so you need some kind of data structure for it to work on. So you can give it an empty branch node of whatever kind of data structure you're working with. So like an empty vector or an empty XML element, but like you do need something. Like say you're dealing with XML, like the minimum you would have to give it is a single tag with nothing in it, and then you can add stuff from there.
Okay, so you create the data structure first, and then you create the zipper from that.
Yeah, so typically you'll have a data structure and you use the zipper to do stuff with it. Yeah. Yeah, I mean, there'll be more time for questions at the end. Just want to make sure that this first part is more or less clear. So, okay, I've given you sort of that first rough mental model of the zipper as that two-element tuple. Now it's time to refine, what a zipper really is. And if you look at the docstring for closure zip, it's a very hicky docstring in that it makes absolute sense if you know exactly what he's talking about. So it says functional hierarchical zipper with navigation, editing, and enumeration, see Huet. And Huet is a French guy, Gérard Huet, who published this article in 1997, Functional Perl, the Zipper, where he says, almost every programmer has faced the problem of representing a tree together with a subtree that is the focus of attention, where that focus may move left, right, up, or down the tree. The zipper is Huet's nifty name for a nifty data structure which fulfills this need. I wish I had known of it when I faced this task, because the solution I came up with was not quite so efficient or elegant as the zipper. It's a pretty cool article. It uses OCaml. It's probably the biggest hurdle to reading it, but I remember reading it a couple years ago. It's a fun read. I can recommend it. So Huet defines two types of data structures. So the first one is the path. And he says a path is like a zipper. And in this case, he's talking about an actual, a zipper like of a hoodie or a jacket. A path is like a zipper, allowing one to rip the tree structure down to a certain location. It contains its list L of left siblings, its father path P, and its list R of right siblings. So it's kind of a recursive definition, right? Because it contains like a sequence of nodes, then a pointer to the previous parent, or its own parent, and then a sequence of other nodes, so the left and the right. There's also a special value, top, which means that we don't have a parent path because we're looking at the top of the structure, so that's kind of a special marker. And then a location in the tree addresses a subtree together with its path. So this is this two-element tuple, which is the current node, with the path, which is the path we just defined. And so here you see where that terminology lock or location comes from. That's from the original article. And so here I have a different visualization. So in these visualizations, there's two types of nodes. There's the diamond-shaped ones, which are the zippers or the paths, and the round ones are regular nodes. And so when I have my zipper over my XML document, it's looking at the root node, so that's that card, and it has that marker that, okay, we're at the top. Now when I go down, now the thing I'm holding is a zipper which is looking at line items with a parent, which is the previous zipper we had, and then left and right siblings. And then I can go down again, and now I'm looking at that product inside the line items, inside the cart. And what you already kind of see here is that the tree's been turned upside down, right? Before we had the card at the top, And now we have the card at the bottom. And the thing that we're holding on to is sort of the place where we're focusing on, the note where we ended up at. And the reason that that's cool is that, say I go right from here, so that means that I'm going to shuffle left, right siblings and current node, like those three pieces of information are going to change, but the parent path and anything down from there remains unchanged. So I can sort of start doing these local operations and sort of not care about anything that's above me in the tree. I hope that makes sense, kind of spatial metaphors.
So is the zipper an abstraction out from the original data structure? Like a way of navigating the original data structure in such a way that all these data structures fit into this way of navigating it?
Kinda. We'll look at Clojure's implementation later, and maybe then it'll make more sense. But so yeah, it's a generic way of prying a nested data structure open, so that you can sort of locally make changes, and then afterwards you sort of put it back together again. So I go down again, and now I'm going to do the same stuff that I did before. I have this chocolate node, and I'm going to replace it with the string luxury chocolate. And now this zipper has turned red, which means that it has a flag set on it, which says that it has changed. Because we said before, the parent and anything, the chain of parent paths doesn't change when you do an operation like this, which means that that product node still has the old value, the old chocolate in it, and not luxury chocolate. Only when we start going up again does Clojure zip rebuild those nodes, and so now product has changed because now it contains a new string. And now line item has changed because it contains a new product. And finally, we're back at the cart. This is maybe the most confusing thing about the whole thing, but again, like, it'll probably become more clear when we get to the implementation. But does it make sense? Should I walk through it again? Okay, keep going. Because here we are at the Clojure implementation. So these vector zip, XML zip, seek zip, in the end they all call this zipper function. So this is sort of the main way to create a zipper, to create a lock. And it takes 4 pieces of information. The first 3 are functions, and the last one is your actual data structure, the root of your tree. And those first 3 functions are a way to tell Clojure how your data structure works, sort of the kind of data structure you're dealing with. So you need to be able to answer answer 2 questions and do 1 operation. You need to be able to have a node and answer, is this a branch node or not? So can it have children or not? When you have a node, you need to be able to say, give me a sequence of all the children of this node. And then finally, you need to be able to do that make node thing where you have a node and a new set of children, and you get a new node which has all attributes of the old node, but with the new children. And if you look at the implementation of Zipper, this is it. So you see that 2-element vector in there, right? So it returns a vector with that root, and with the nil, which is what Clojure uses as its marker to say we're at the top, right? So the path is nil because there's no parent path because we're at the top. The other thing to notice here is that it then attaches a bunch of metadata to that vector. So these functions that you passed in there get stored on that 2-element vector as metadata. So this is pretty neat. It's a neat trick, and I haven't seen it in many other places. Yeah, now if you look at vector zip, so vector zip just calls zipper. In the case of a vector zip, a root is a branch node if it's a vector. Otherwise, we'll consider it a child node. Seek just gives the stuff inside the vector. And then the make node function mostly just calls vec on the children, and in this case, it also just makes sure it preserves metadata. So far, it's fairly straightforward. And then if you look at the implementation of the actual Clojure zip branch function, Clojure zip children, Clojure zip make node, they look up those specific functions on the metadata and call those. So this is kind of a pretty neat way of doing polymorphism. So Clojure has protocols, Clojure has multi-methods, which are all different ways of, dispatching to different implementations based on the specific value that you're looking at. But this is kind of yet another way of doing it. And so vector zip, on that zipper, you see that all it really does is just wrap it in a vector and then add a nil. If you look at the metadata, you see those functions there. So it's kind of, nothing under the covers. It's fairly straightforward once you know what's going on.
I just want to butt in for a second and say, wow, that's really cool.
It's neat, right? Yeah. Yeah, so even if you never use zippers, maybe you end up using this trick. So now we can actually start looking at the values returned from these function calls. So now I'm going to walk through that first example again with a vector zip. So after turning it into a zipper, it's just this 2-element vector. And then you go down, and so now you see that the node we're looking at is the 1, 2, and the parent path, or the path at the moment has this left siblings, right siblings, and a parent path, which is currently nil, which is, because the parent of the node we're looking at is the root. And then the Clojure also stores a sequence of parent nodes, which it uses to reconstitute, sort of rebuild the values as you go back up again. So you can already see if I go left or right here, that left and right and the current node changes, but everything else changes, stays the same. Now I go down one more level, and you start seeing this linked structure. So we have, we're looking at the 3 now. It has left and right siblings, and it has a parent path, which is the one we just had, right? So here we have left 1, 2, p nodes, p path nil, r nil. That's inside there now. This is the parent path of the new path. And again, we can sort of go left and right, and all it needs to do is change those siblings. Everything else stays the same. Now I append the child. It's gotten that extra marker at the bottom. It's changed now. But you see that X is now in the node that we're currently looking at. But if you look, for instance, at the parent nodes, that X isn't there. Not yet, right? So Clojure has been able to make this local change, and so that's kind of one of the benefits, the efficiency benefits of zippers, that you can go deep into your structure, make a bunch of changes, and then only pay the price of rebuilding your path up to the root when you zip back up. And so we'll do that now. Once you start going up, you can see that it starts building up those values again. And I'm actually doing better on time than I guess I really flew through this. Slide 100. Okay, two more libraries I want to at least mention. One is FastZip. And FastZip is really just what it says on the tin. It's a faster zipper. So the Clojure implementation with the vectors and the metadata, it's super cool. It's also nice that you can just inspect it, that it's just a vector, and you can sort of look at those values. So I do typically develop with Clojure zip, but then, when you want to ship this in production and you want to get those extra cycles out, you just swap out Clojure zip for FastZip. It's absolutely the same API, but it uses def type under the hood, so it really gives you this high, native dispatch. The only thing to watch out for is that you don't rely on implementation details. So now you all know that a Clojure zip is a 2-element vector, but if you start relying and, for instance, destructure that vector, yeah, that's not going to work with FastZip. But as long as you stick to just the functions in Clojure zip, it should work 100% the same. Clojure and Clojure script, by the way, all of these are cross-platform. And then the final thing I want to mention is rewrite CLJ, because this is one of the libraries that builds on top of zippers. And in this case in particular, it gives you a zipper over a Clojure syntax tree. So what rewrite CLJ does is it parses Clojure source code, turns it into a syntax tree that preserves formatting and white space. And so you can process that, do stuff with it, make modifications without messing up people's formatting. And so a lot of tools use this. You might have come across CLJ format, zprint, line agent, refactor nREPL, mutant, mutation testing, like all of these use this rewrite CLJ under the hood. Rewrite CLJ has its own .zip namespace, which largely an API corresponds with Clojure zip. But for instance, if in rewrite CLJ you go next or you go right, it's going to skip over white space nodes, which is most of the time what you want. So you can sort of deal with that AST and ignore the white space, but it is still there when you build it up, you turn it back into text, the formatting is still there. You also get some extra goodies, like some extra functions that are particular to dealing with source code. So this is a pretty nice library. And so, because yeah, people keep asking me, okay, yeah, but I've looked at these zippers, but what do you use them for? So this is, for instance, one real use case that I used them for not too long ago. So we, project that's a year or two old, we started out with a certain namespace organization, and then sort of halfway through decided to have a bit more of a thought out namespace organization with proper reverse domain name and all of that stuff. But so we had about 50% of our code using the old scheme and the new scheme. And at a certain point, we wanted to clean that all up. But at the same time, it kind of had to all happen as a big bang thing, because you don't want to block everyone who's working on this. So the solution was to write a script which goes over the complete code base, updates all require statements, updates all namespace keywords, all that kind of stuff, so that we can sort of find an opportune moment, merge as much as possible, run this once, get it over with. And so this is one function in there which it uses, so you see there's a loop recur, which takes the input zipper and then just goes next, next, next. So it goes over the complete source code until it's either at the end, then it stops, or if it's looking at a list and the first element in that list is a require keyword, in that case, it goes down into the list and passes the zipper to another function which will do the actual updating of the requires. So this is one example of what zippers in the real world might look like. And this is kind of my last slide, but since I didn't go as much over time as I thought I would, there's one more thing that I used zippers for recently. So I was working on a project which kind of does sort of a Jupyter notebook kind of interface. So these are these environments in a web browser where you can evaluate code. And so we had streaming output from the server to the client. And there's two things that are tricky with that, because you kind of need to emulate a REPL like a terminal. So you need to deal with ANSI escape codes, but you also need to deal with carriage returns. Like if you have, for instance, a progress bar, like that would work in a terminal, then you kind of need to emulate that in your HTML. Like if you come across a carriage return, go back to the beginning of the line, where the beginning of the line in this case is actually like a bunch of spans that are encoding your color stuff. So there, I extensively used zippers to sort of navigate back, okay, where is actually the beginning of the line, split this up. So that was another use case. Yeah, and that's all I have. But I am here for questions.
Questions? Yes.
I kind of want to ask about like possible extensions to the zipper idea. I think it's cool. And like, what if you wanted a zipper except with 2 pointers, or what if you wanted a zipper that instead of tree data structures worked on directed acyclic graphs or general graphs? Do you have any ideas?
Oh, that's an interesting research topic. I mean, so I think the reason that zippers came to be is the idea of. So actually, I have this one more slide here. So I kind of briefly mentioned this in passing, but it's the idea of, so if here are two different ways of doing the same thing, right? So the bottom one, I'm just sort of using closures assoc in to replace a value deep inside a tree, whereas the top one, I'm doing the same thing with zippers. And in this case, I mean, both do the exact same thing. But if you have a bunch of those assocs in, so each time closure needs to go from the top to the bottom, make that change, and then so you end up with the data structure on the right, which reuses a lot on the left, but anything from your position where you made the change up to the root, those will all be new nodes. And so if you do a bunch of updates every single time, you're rebuilding that path from your current position to the root. And that's really what, why zippers shine. It's kind of because you can defer that cost as much as possible. So in a more general graph structure, I don't know, I can't answer on the top of my head, if you can do the same. I mean, I guess if you have if your directed acyclic graph still has the concept of a root that you consider the root, because you still want to do it in kind of a functional way, then I guess you can do something similar. Having two pointers at the same time, I think this is going to start getting very, very tricky. You're going to have to do a lot of bookkeeping, and I don't know if it's still, I guess it also to see if there's a use case for it. Might be possible. Yeah?
Would you say that the benefits of using zippers scale? Would you say that the benefits of using zippers scale with the number of changes that you need to make deep inside of some nested structure?
I mean, that's one of the benefits of zippers is the performance gain. And so yes, performance-wise, you're going to get more bang for your buck the more that you can, cluster operations together, sort of, navigate to a certain position, do your changes there, and then only zip up once. But I think the other thing, people that use zippers, I don't think performance is often the first reason. I think the main reason is that there's certain problems where this navigation API is just very elegant. And so that's probably the main reason that people choose zippers.
Anyone? Bueller?
All right, well, I'll be here. Happy to chat later.
Thank you.
Thank you all very much.
That was great. Appreciate it. And so, just because I don't think we were streaming then, Arna, how do I pronounce your name? Sorry.
Arna.
Arna.
Yeah,
Okay.
Arna. Yeah, Arna.
You do freelance closure consulting. Are you looking for more clients?
Actually, not right now. I mean, I'm always happy to talk. There might be interesting stuff, especially when it comes to training with some people in Berlin.
So someone maybe could get on your wait list. Yeah.
Absolutely. So, but I actually just recently said goodbye to a consulting gig because I want to spend some time on Lambda Island. I got some open source work that I committed to now with Closures Together. I'm also organizing a conference next year. It might be a little bit far for most of you. It's going to be in Belgium, Heart of Closure, but it's going to be an absolutely kick-ass conference early August. So I'm going to be busy the next year is what I'm saying.
I'm going to be out in Belgium speaking at a conference in 2 weeks. Can you maybe schedule it for then? No, that's great.
Yeah,
I've never
awesome.
been to Belgium, so I'll check it out. I'll pre-scout it for next year's closure conference.
Yeah, that'd be awesome.
That's great. Cool. Well, thank you for speaking for us, and I appreciate your help.